So, why can a galaxy be carried away faster than light without breaking Einstein's speed limit? In the Hubble ultra-deep field, some faint smudges are so far away that light they emit today will never reach us. Special relativity, the part of Einstein's theory that ignores gravity, says that in any small neighborhood of space and time, no object and no message can outrun a nearby light beam. That local rule is tested in laboratories and with precision clocks on fast aircraft. But a distant galaxy is not in the same local neighborhood. Gravity makes spacetime, the combined system of space and time, curve and evolve, and the speed of a faraway thing depends on how you define distance across that curved spacetime. The puzzle is deciding what is actually changing when the separation grows faster than light. Cosmic expansion is not galaxies blasting through pre-existing space. In general relativity, the geometry of spacetime can stretch, so galaxies can stay nearly at rest with respect to that stretching while the distance between them increases. Picture a long string of rulers laid between two galaxies, and then picture every ruler slowly getting longer. The endpoints hardly move locally, yet the total measured distance grows. Because the stretching happens everywhere, no galaxy sits at a special center, and every observer sees distant galaxies recede. And because electromagnetism and gravity can bind matter, atoms, planets, and even whole galaxies do not participate in the expansion in any measurable way. Once distance growth is the main effect, it becomes plausible that the growth rate of a very large distance could exceed light speed without anything locally outrunning light. How can we measure that stretching if galaxies barely shift position during a human lifetime? We use redshift. Light from distant galaxies arrives with a longer wavelength, meaning the peaks of the light wave are spaced farther apart. Atoms produce spectral lines, sharp fingerprints at specific colors, and astronomers see those fingerprints displaced toward red as distance increases. Some redshift is Doppler shift, produced by motion through space, but in cosmology the dominant effect is that expanding space stretches a light wave while it travels. This is observationally confirmed by the consistent distance versus redshift pattern across galaxy surveys and by the cosmic microwave background spectrum. A counterintuitive implication is that the photon's energy drops as its wavelength grows, and in an evolving spacetime there is no single global place where that energy goes, even though energy is conserved locally. So, the numbers that look like superluminal speeds come directly from how much the universe has stretched the light between us and the source. A photon can start from a galaxy whose current recession is faster than light and still reach your telescope. Locally, the photon always moves at light speed, but the distance it still has to cover can increase if the space ahead expands quickly enough. The Hubble radius is the distance where today's expansion rate makes the recession equal light speed, and it changes over cosmic time. Early on, matter's gravity slowed the expansion over time, so the Hubble radius grew, and light that initially lost ground could later start gaining. That is why we see the cosmic microwave background, released when the universe was about 380,000 years old, even though that emitting region is now about 46 billion light-years away, with a light-year being the distance light travels in a year. So, faster than light does not automatically mean invisible, which forces us to ask what kind of boundary would truly block signals. So, is there any distance that really is a one-way boundary? In a universe whose expansion is accelerating, there's a cosmic event horizon. Beyond a certain distance, light emitted now will never reach us. Acceleration is observationally inferred from distant type Ia supernovae, which look dimmer than they would in a steadily slowing universe, and that inference matches other probes of cosmic geometry. The simplest fit introduces dark energy, meaning something that keeps the expansion from slowing. We measure its effect, even if its underlying physics is unclear. Here's the consequence. A radio signal aimed today at a sufficiently distant galaxy will never arrive, because the space the wave must cross keeps growing faster than the wave can make headway. This is why the observable universe is defined not by where matter ends, but by our past light cone, the region from which light has had time to reach us so far, even though we cannot exchange signals with everything in it. Faster than light recession is not a way around relativity. It is one reason horizons exist at all. Einstein's speed limit survives because it is local. In any small region of spacetime, light is the fastest signal, so no rocket and no radio wave can outrun a nearby light beam. But the distance to a far galaxy is a chain of many small regions, and in an expanding universe that chain can lengthen so quickly that the total separation grows faster than light could cross it. That is, faster than light recession. Not motion through space, but growth of space between. It also explains the opening T's. Those faint deep field galaxies can be receding faster than light while still visible, and some regions will never send us new light. In fact, most of the observable universe is already in that regime today. Like, if this was interesting, hit the subscribe for more and turn that notification bell on.